over required moment, which is the factor load moment, is very close to 1. That's by design. I wanted it that way, so that we can see the difference between IS 456 design and ACI design. This is perfectly matching, so IS 4, at least that's what I think. Now let's go over ACI 318. Okay. So in this, the same assumptions, we are all familiar with this. Equilibrium in each section must be established. Perfect bond between steel and reinforcement, which is good. Plane sections remain plane after bending, which means you will have a linear strain diagram. All these things are very, it's not new to you. Tensile strength of concrete is ignored below the neutral axis. Then we use bilinear stress strain curve for at least for ACI method. And then maximum usable strain for axial compression is 0.002, and for flexural compression it's 0.003 as opposed to 0.0035. Okay, that's the difference. 0.003 is what we use, but like I said, it doesn't make any difference. It doesn't. In the end, it won't make much difference. And then members are classified as beam. I don't remember seeing any IS 456 requirement where they define this. I don't know, maybe they do, but I don't know, I haven't seen it. So if my axial load is less than 10% of area of the cross section times F prime C, which is the cylinder compressive strength on 28-day compressive strength. If it is less than that, then only I can use beam design equations. If it is more than that, I must use beam column methods. Okay. So same thing, we have the strain diagram, linear strain diagram, and also the compressive stress is parabolic. And then we have the strain. Actually, we don't use strain beyond 0.003 for concrete, but for steel we'll use bilinear stress strain curve. That's the idealized stress strain curve, bilinear stress strain curve. Exactly same until this point. Now we are going to deviate, okay, from whatever we have done so far. What we will do is the ACI simplifies the stress diagram to be a rectangular stress diagram, because rectangular stress diagram with rectangular section is so simple to work with. And even if you use the most complicated stress strain curve, and find out the moment strength and compare it with this stress block with only rectangular stress block, the difference is less than 1%. So why even bother? Make it simple. That's what, if you see ACI requirements, everything is simplified so that anybody who has a little bit of knowledge can actually do the design. Very, very simple. Okay, so we have rectangular stress block. Okay, now one thing you must remember is this maximum strain is 0.003, and here this rectangular stress block will not go all the way to the axis. It's terminated a little bit before you reach the origin. Okay, so when you rotate this and flip it, you will see this rectangular stress block. Here we have average stress. These are 2 or 3 things. If you can remember, you don't even need a book. You can just calculate everything without a book. Remember, you just have to remember just a couple of things. Okay, one of those things is the average stress is 0.85 F prime C. Big deviation from IS 456. How much did we use there? That's right. Big difference. Almost. Yes. 0.444. That's what I think we used. FCK. Of course, there is a small difference between FCK and F prime C, but even then, there is a big difference here. Okay. And what's this depth? This depth is depth of the compression block, and it's known as lowercase a, which is small letter a, is what is used for this depth of the compression block. And that depth of the compression block varies. That means this depth to this depth varies, the ratio varies with F prime C. That means concrete strength. Okay? So smaller the concrete strength, larger the ratio. So 4000 psi concrete, which is about 27.5 MPa. For that, this is 0.85. 0.85 times the depth to neutral axis. From here to here is depth to neutral axis, C. That's what in IS 456 we call it X sub U, right? That's what we call it. Here we call it C. And from here to here is A. So the ratio of A to C is 0.85 for lower strength concretes. And for higher strength concretes, it's smaller. That means this stress block will terminate here, 0.65 for 8000 psi concrete, which is about 55 MPa concrete. Okay? So these differences, this 0.85 F prime C and the difference, the IS 456 uses 0.444 FCK. What difference does that make? Just from your basic knowledge of section analysis, what do you think that will be, or what difference do you think it will make?
50%.
Yes, 50%, but what is that?
Considering additional factor of safety.
Right, yeah, that's correct. But what I'm saying is, instead of 0.85, if I use 0.444 F prime C, or F prime CK, or FCK, what difference does it make in this stress diagram? Obviously, the depth of the neutral axis will come down, because instead of using 0.85, if you have a rectangular rectangular section, if the same section is used and you are analyzing with two different methods, because this is 0.85 F prime C, this depth of the compression block is smaller. Do you see what I'm saying? Compared to
It's a higher under-reinforced section in SEA.
Very good. That's the very good point. That's what I was trying to come to. Okay, so you're actually, in case of ACI stress block, we are using higher stress, average stress, and therefore it's likely to be more under-reinforced. Whereas in IS 456, without our knowledge, we are pushing this neutral axis downward. That means we are making it more and more over-reinforced section. So that, I have not done real numbers, but that's something that is striking to me right now, and if you do a calculation, you'll see that may make a little bit of difference. Okay? And then also, because this is a smaller depth, my resultant force is also at a higher level, and therefore it should give me a larger moment strength. Does it make sense? Because the moment arm is larger. Okay, so that may make a difference. So that's the reason you have to be careful not to jump into ACI 440.1 and just use it and then apply same load factors and then call it safe or call it consistent with IS 456. There will be some difference. So remember this rectangular stress block, very simple to work with, average stress of 0.85 F prime C. This depth is A, my width is B, this width is B. If it is uniform, I can just find out the total compressive force without any equations. I just look at it, I can write down the compressive force from understanding rather than memorizing. Okay? So this is what it will look like. You have actual stress block in 3 dimensions, something like this. We will have a uniform stress block, something like this. So you cut a section, this is what you will see. The actual is parabolic, but our idealized is rectangular. This depth from here to here is the moment arm. Am I speaking too fast? Okay, good. So from here to here, d minus a over 2 is the moment arm, and then we can find out the moment quite easily. Okay. Now, what is the relationship between depth of the compression block? Remember, the compression block is rectangular in shape, and depth to neutral axis. So those two don't coincide. right? Here. This neutral axis is below the depth of the compression block. That's a little bit below. So there is a relationship between this and this. The relationship is this depth A equals beta 1 times C. We will define what beta 1 is. Beta 1 is, those of you who are familiar with Hognestad method and others, you know that there are two factors, alpha and beta, for defining any stress. Those are the stress block parameters, right? Some of you know that because I already talked with you. So in case of ACI, we don't want to go there, but if you need to, that will be a good way to go. Beta 1 is what will relate A and C. And beta 1 is dependent on, I already mentioned this. Beta 1 is dependent on concrete strength. Okay? Stronger the material, smaller the beta 1. Weaker the material, like 4000 psi concrete, the beta 1 is 0.85. Or 4000, let me, 4000, yeah, I have it here. So I have the conversion here. For F prime C of 17.24, which is highly unlikely. No one uses this low grades concrete in most of the structural work in the Western world. This one here is 17.24. Mostly you'll use at least 2,500 footings or 3,000 for footings. But for actual suspended work like beams, columns, slabs, you'll at least use 4,000. For typical bridge decks, you use 4,000. Okay? So that's 27.58 MPa. For some reason, IS 456 uses much lower strengths than 27.58, right? You start with M20. So M20, 20 times 0.8 is 16. So we are starting below 2,500. I don't know why. I think that needs to be raised. It will be a good idea to raise that minimum compressive strength from that 16 to maybe 20 or something like that. So M25 should be the minimum or something like that. But anyway, so for 4000 psi, that's 27.58 concrete, beta 1 is 0.85. For 55 MPa concrete, it's 0.65. Anywhere in between, do a linear interpolation. Okay?
But as per standard design, we are considering target strength is 26.6.
No, target strength is different. Target strength is for batching, right? Quality control, exactly. So ACI, in addition to F prime C, there is additional margin for quality, yes. So this is your design value. Just like your characteristic value, this is the design value.
ACI is not considered as quality?
Yes, they do. But what they do is they're asking the supplier to make a concrete which will have statistically larger mean, so that when you supply to the site, we have a guaranteed compressive strength of whatever this is. So you are right, that's a good point. So there is another layer there. But that's not in here because in design we don't want to consider that. That is the supplier end of the equation. Good point.
That aspect is there in IS 406,
Yeah.
but we are not following it. Supply not following it.
Right.
Statistical mean is
Yes,
there.
yes,
It's there in IS.
I'm sure it is there. Right.
As you say, it's not, we are not following it.
The compliance is
Compliance is very,
very, yeah. But I'm sure in some major projects they do that.
Yeah.
So, like I said, you don't have to remember anything. All that you have to do is what is total compressive force, what is total tensile force. The total compressive force is, remember, average stress is 0.85 F prime C, and depth of the compression block is A, and the width of the uniform width of the beam, in this case rectangular section, is B. So that's our total compressive force. Do you have to refer to any text for this? Absolutely not. All that you have to do is remember that average stress is 0.85 F prime C. Perfect. What about the steel force? Steel force is area times Fy. Fy is the yield strength of the material. That's it. There is no partial material factors in this. Okay? That's the difference, big difference. Then you find out in this equation, all that we don't know is depth of the compression block A, and therefore you can find out depth of the compression block by just rearranging the terms, and this is what you get. A equals rho times FYD over 0.85 F prime C. Does anyone remember? Okay, let's say what is 1 over 1.85? Close to 1.15. Okay, probably it's 1.15. Yeah, it's 1.15, right? Do you remember what we had here for IS 456? Big difference. That's a big difference. And then you find out the moment strength based on effective depth minus A over 2 times total tensile force. Or you can use D minus A over 2, which is the moment arm, times the total compressive force 0.85 F prime C times A times B. Either one is fine. Okay, now that you got your nominal, this is nominal, and for nominal strength, phi mn is design moment strength. And we always work with design moment strength. Design moment strength needs to be greater than factored load effect. Now I need to introduce you to a few things. First of all, we had to find out phi factor, right? I didn't talk about phi factor yet. We will use phi factor in our ACI 440.12 for FRP bars. Therefore, I need to introduce this to you really well. I need to explain this well. Let's say this is my beam. It has some width, effective depth of D. Okay? And then we have reinforcement in 2 layers. My strain diagram is this. Okay? Strain here is 0.003. That's our reference strain, always. Regardless of what design you are doing in ACI, this is 0.003. IS 456, we use 0.0035, which is fine. And then this is the depth to neutral axis, C. And then you draw the strain diagram and extend it to the level of the steel. The bottommost layer of steel, remember that, bottommost layer of steel is referenced as D sub T. The average level is just D without any subscript. The bottommost layer is D sub T. So when you are designing with ACI and you are finding out phi factor, you are finding out the strain at the bottommost layer of steel. Very important difference. It's a minor, it's not complicated, but it is very important. Now the phi factor is based on the strain at the bottommost layer of steel. So the strain reference is to the bottommost layer of steel, which is dt from the top fiber, and the strain at that bottommost layer of steel is epsilon t. So epsilon t is the bottommost strain in the bottommost layer of steel. I'm going back one more time. Here, this strain is epsilon t at the level of bottommost layer of steel. Now I'll introduce you to 3 things. One is what's known as compression controlled condition. The other one is tension controlled condition. 2. The third one is maximum reinforcement requirement. So there are 3 strain limits actually ACI tells us to use. If my beam is lightly reinforced, we can get very large strains at the bottommost layer of steel. And that large strain is defined as 0.005. I think we had 0.0038 here for IS 456. I think there is a reason why they have that smaller value. Because your depth to neutral axis is larger, therefore, if you want to satisfy this 0.005, you'll be struggling with it. Does it make any sense? I don't know if you understood what I said. Did you understand what I said? Because our neutral axis depth for the same section, if you are designing by IS 456, will be larger compared to the neutral axis depth using ACI section. Larger the neutral axis depth to neutral axis, smaller the strain in your steel. So if I have larger limit for the steel, you will be struggling to design a good section. That's the reason they have a smaller value, I think. That's what I think. That's what I think. I may be wrong. So this is 0.005, and that's considered as tension controlled section. this other limit is epsilon t equals epsilon ty. Epsilon ty is the yield strain for the bars. Okay, how much time do we have? Half an hour. Okay, very good. So I can finish this. Yeah. So this other limit is epsilon t, which is epsilon ty. Epsilon ty is the yield strain of the steel. So for a 60 grade steel, which is about 415 MPa, what is epsilon y? About 0.002. Do you agree? So for a 60 grade steel with E equals 29,000 KSI, that's in KSI units, but in SI units, about 415 MPa with 200 GPa modulus, you will see the strain, yield strain is 0.002. So this can be about 0.002. But now ACI has opened up the use of higher grade steels. Therefore, they don't say this is 0.002. They say it's epsilon ty. Because for higher grade steels, like if you have 100 grade steel or 120 grade steel, which is 800 MPa steel, then this will be 0.004. Okay, so it is dependent on the grade of your steel. So the minimum, one of the limits is epsilon ty, and ACI tells us, this is written nowhere in this manner, but I can explain this to you here this way, so it becomes easier for you to remember. ACI requires you to maintain a strain of at least 0.004 to classify a member to be a beam. In other words, it's trying to make sure your steel has yielded adequately. So minimum strain, not tension controlled strain. Minimum strain in bottommost layer of steel is 0.004 to classify the to be a beam. If it doesn't satisfy this requirement, then you have to design it as a beam column or something else. But if you are designing a beam, you must have a strain of at least 0.004. So the phi factor varies from 0.65 for ordinary beams to 0.9. 0.9 is when you have epsilon t of 0.005 or greater. So minimum of 0.005 will give you a phi factor of 0.9. Larger the phi factor, larger the utilization of strength, right? And why are we able to utilize larger strength? Because of the ductility. Because the beam is able to deflect significantly while maintaining the load carrying capacity. That's the reason if my epsilon t is 0.005 or greater, I can use a larger phi factor of 0.9. But I have a limit here. 0.004 is the limit for a beam. So if I'm designing a beam, it must have epsilon t of 0.004. Therefore, for that, this value is for a 60 grade steel, that would be 0.817. Okay? So phi factor practically will range from 0.816 to 0.9 for a 60 grade normal grade steel. Okay? So there are some equations just for linear interpolation, but that's so simple, it's just algebra. So epsilon ty is the yield strain Fy over Es, and for 415 MPa concrete steel, 415 MPa steel, epsilon t will be 0.002. And you have a transition zone between compression control. So I'll repeat myself one time. Anything up to here, if my strain in the bottommost layer of steel is less than equal to epsilon ty, that's known as compression control failure. That's a brittle failure. Okay? And remember this phi factor, it's 0.65. And also remember, many times I said for FRP reinforced beams, we prefer over reinforced condition. So I haven't even presented anything on FRP beam design yet. But I'll ask you a question. What would be the phi factor for FRP reinforced beams if it is a over reinforced condition? 0.65, right? That's the basis for the phi factor. So this 0.65 is what we will use in FRP reinforced design for an over-reinforced condition. For an under-reinforced condition, we'll use 0.55, which is even smaller than 0.65. Okay? Okay, so we have a transition zone where you can use this equation to find out the phi factor. It will be between 0.82 and 0.9. So not much variation. So they are in the table form here. This is just for your reference. So what about the other two conditions? Anytime you design a beam, there are three things you want to do. One is, number one, for moment strength, you design for the moment strength, right? So you find out the moment capacity or moment of resistance. That's what IS 456 calls it, moment of resistance, but it's the moment capacity is the same thing. That's one thing. Number two is minimum area of steel, and number three is maximum area of steel. These are the three things you must check for any beam design. So there is a minimum area of steel mentioned in the ACI code. There are two simple equations. These are in PSI units. F prime C must be in PSI units. Fy needs to be in PSI units. Okay, and then here also Fy should be PSI units. But in my example, I will give you MPa equivalents. So everything refers to bottommost layer of steel for phi factor. For phi factor, epsilon T is referred to the bottommost layer of steel. For moment strength, we refer to the average location. So if I am finding out moment strength, my D will be from here to mid height of these two layers. That would be for moment strength. Whereas if I am finding out phi factor or maximum reinforcement, that's based on the strain at the bottommost layer of steel. Does it make sense? Do you see the difference? Okay, D and D sub T, that's the difference. Okay,